So when we're dealing with the data and we want to start comparing data sets, if we have two data sets, we can use a t-test, and it's very useful and a very good way of comparing means. But let's say we want to compare more than two. The t-test itself isn't designed to handle that, and so you're going to have to go to something called an analysis of variance or an ANOVA. So typically, if you have three or more data sets, then that's what you are going to use. So let's say, for example, I want to compare 2023. So all of the mass data for salicylic acid, for example, I want to compare that from 2023 to 2022. So I want to compare the 2 years. I've only got two sample sets, so I can use a t-test on this and get a very rigorous result out of it. However, if I want to compare all of the years to each other, so the mean of 2017 to the mean of 2018 to the mean of 2019 to the mean of 2020 to 2020 was COVID. We were shut down, so we have no data. 2021 and 2022 and 2023, we have to use an analysis of variance. So that's essentially what we're going to do. Now, the best that the ANOVA can do for us is just tell us whether the means are the same or not. They actually can't tell us which means are different from each other, and that's where plotting the data can help out as well. So first, we can have a statistical inference to see if the means are all the same or if they are not. And if we want to see what means are potentially different, we can plot the data and actually see which ones look to be extremely different from others. And then we can say do a t-test on those specific values. So we can use it to kind of hone in. There are other statistical analysis that we're gonna that are not part of this course or program that you can get into. I think it's called Tucky's HSD or something. I can't remember the name of it, but there's a couple of others, but it gets more complicated, much more complicated, and is not part of the scope of the work that we're going to do today. So when we want to analyze this data, we've got several ways of doing it, and it depends on the library that we're going to choose. And I have show a couple of examples up here. But the first thing we want to do is we want to decide what we want to compare. So in this case, I want to compare lab days. So I want A versus B versus C, and I want to get the mass of, say, either salicylic or crude ASA. One of these columns, we'll figure it out. and But I want to compare each of them, and I want to see if the values are the same. Now remember, when the value comes out, when the stat comes out, it's just going to tell us whether all of them are the same or whether all of them are different. That's about it, and we don't know which ones are different. So the assumption with it is that all the means are the same. And so if the p-value comes out to be less than 0.05, then that means that the means are not the same. And you could have one value that's out of 17 values, let's say, and that mean is not the same as the rest of them, and therefore the ANOVA is coming back saying that the means are not, all the means are not the same. So determining which one of those is not the same, that's where we would come into the visualization and have some graphs and charts to help us figure out what that might be. We could also just output the means, make a table of that, and then actually see which one's the largest, and actually just do some manipulation that way with the data. So let's take a look at some examples. These are fully done already, but I apologize. What I wanted to point out was the fact that here we're using SciPy as stats, but really it's SciPy here is the key. I didn't have to put all the rest of this. I could have just imported SciPy. We're reading a data frame of this data set here, so we're adding it to the variable data. And so now we're going to group it. So now that we've made this data frame here, we're going to group it by lab day, which is what we wanted. So now we're going to get those different columns, A, B, C, D. And if we were to print this out right now, we would see a new set of information that's here just based on lab day. But now that we've got the group data, now we can perform the t-test. And this is coming from the stats model. So right there, so we imported SciPy as stats. So there it is coming in from the SciPy. And so it wants an F value, a P value, and it's going to do a one-way ANOVA, which is what we're looking for. And we want to do it on the mass of crude ASA. So we want to see from lab group to lab group, is the mass of ASA that they're producing the same? We're also going to have to drop any null values because the if we've got them, then the calculation won't work. And there's a bit of a for loop here. And instead of the usual we would see where for, and then we would have something underneath like this, it's all grouped in one line. So it's very, very efficient code to do this work. So there's all the work we need. Now we're just going to print out the values. So the f value is going to be this, the p value will be this, and it'll even tell us if the p value is less than 0.05, then the means are not equal, and if all else, then they're equal. So it's when we actually run it, we see that the p-value is very, very small, 10 to the negative 12, so the means are not equal. So out of all the means from lab group A through to lab group, I think it's P or R, I can't remember, um, something is not equivalent to the rest of them. And so we don't know which ones those are, but we can at least say that we could have a bunch of means here, and then one is out of spec, and then here like this. And then what this ANOVA is telling us is that something is out of spec, but we don't know what it is. So you can see ANOVA can be useful for that type of information, but for pinpointing what it is, we don't know. So we got another one here using SciPy, so just pay attention to the grouping and everything we're doing here. So with this, we're going to use SciPy and we're going to do the F1 way, which is exactly what we did in the previous one. It could have just run with SciPy and everything would have been good. We're going to read in the CSV file, and here we're going to drop the NA right off the bat. Now this is a little, not going to say problematic, but notice the difference in the p value here, okay? So we're 2.4, and over here it's 8 times 10 to the negative 12. Part of that difference is because here we're dropping the null values of the entire data set. So anything at all that's missing in any of the columns, we will completely remove that row. And we're seeing the effect here, the difference right here. So this previous one, we can see the drop NA was only for the massive crude ASA. So if there was a missing value, it got rid of just that value because it didn't care about anything else. So it grouped everything by lab day, group the ASA values, and get rid of any missing ASA values. And so only those ones would be gone. And so the p value is based off that. This one here is a little more dramatic. It drops all of our NAs, all the null values from everywhere. And so our data set is actually more affected than it should be. And we'll see that's our p-value. Overall, the result is the same, but just note that there's a difference in when you apply this drop null value. So we're putting everything into groups. And we're using a group lab day and mass ASA, and we're going to create a list based off of that. And now that we've got the list done, we can now perform the exact same thing that we just did on the previous one. So the calculation is still the same. We're going to get an F statistic, a p-value. We're doing the one way, the F1 way, and we're going to do it on groups, which we've now defined that variable right here, which is a group that's based on lab day, and then this data set here is what we want. It's going to print out the statistic and the p-value, and it's got a nice little sort of thing here to tell us if it's less than 0.05 or greater than 0.05. So it says here there is a significant difference between the groups. So even here, the printout was different than here. So the means are not equal. There is a significant difference between the groups. So it means the same thing. It's just written differently. Now, most of this I did in AI. So I was using Copilot. And so when I pull in the data set and tell it what I want to do, this is where the variations come through. And this is where it's important for you to decide and understand what's happening along the way. And what you can do is you can actually then pull in this code again, this entire code. I could copy and paste, put it back into Copilot and say, what does this do? Or I could go to very individual things here and ask Copilot exactly what does this thing do, and it'd give me some information on that. Last one here. So this is now using the stats model. So there's still SciPy, but it also is using stats models library. So there's stats model API as SM, formula API OLS. This apparently is the important one. So right from the bat, we're gonna call in the CSV file as a pandas data frame right here. So we're gonna apply it to this variable data, and now we're gonna work on it. And so using the model, so we're creating another variable called model, and then there's OLS. I actually am not sure what this stands for, and if I go to Copilot, it could explain to me what this OLS is. But you can see that the coding is very different. I would not have known how to do this, and even the syntax here. Here's an open bracket, then a single quote, mass crude ASA, this tilde. a C, and then lab date, and then a final thing here. But there's no end bracket. Oh, it's over here. The end bracket's over here. So this to me was a very confusing one. I let AI do it for me, and then there's dot fit. So within one of these, either SciPy or stats models, is this OLS and then the dot fit function that's being applied to it. And so now it creates an ANOVA table for us, which outputs this information. And the important one for us is that based on lab day, the means are not the same. So we're getting 8 times 10 to the negative 12. Let's see if any of these are the same. So this is the one where the drop NA was an issue. And here, 8 times 10 to the negative 12. So this value here we're getting is the same, it looks like, as this one. So even the F value, 6.4, and the F value here is 6.4. So this calculation and this calculation are the same. Note that here we did a drop NA on the very specific values within that one column. Here we did not. We did drop NA on all the columns, so our P value and F value changed significantly. But here we didn't do a drop NA. So this stats model already has it built in, so it'll probably drop or omit any missing values. So some stats models will do that for you. A good example is that descriptive function to give us all the information. We can actually apply that on a float values and it will skip the missing values. We don't have to do a drop NA technically. It's good practice because when you skip ahead to some of these other fancier statistics, some of them require you to drop the null values. Some of them have it built in where it skips it like this one. Okay. Um, my suggestion is to go with this method right here. I think this one is a little bit better. You could also do this one. I also like this one as well. The only difference here is put the drop NA over here, which essentially ends up with the same, almost the same thing. All right, so I would have the drop NA specific to here somehow. So even the drop NA, if you were just to apply it just to the mass crude ASA, um, then group by lab day and mass crude ASA after that, and that would work pretty good as well. Okay.